This is Doc Nylund bringing you a video on Lenz's law. If you have not watched my video on Faraday's law, please watch that video first. Emil Lenz is the gentleman in the illustration, and he was born in 1804. There's actually a lunar crater on the moon named after him, which is pretty interesting. In this video, I will present a thought experiment that involves Faraday's law and exposes the need for Lenz's law. This can be a tricky topic for students, so be sure to pay close attention and let's get started. Let's imagine we have a rectangular loop of wire that has been placed inside a uniform magnetic field. Let's imagine that the magnetic field is pointing out of the page as shown in the illustration. Lastly, imagine that one end of the loop is free to slide, as seen on the right end of the loop in the illustration. So at this point, the magnetic field strength is constant, the area of the loop is constant, and the angle between the two is constant. As a result, the magnetic flux is constant and no induced current will flow. Now let's imagine that we begin sliding the free end of the loop to the left, as shown in the illustration. This sliding is going to change the area of the loop, and therefore change the magnetic flux. Now, according to Faraday's law, a change in magnetic flux will create an electromotive force, which then causes the electric current to flow. So in our case, decreasing the area of the loop will decrease the magnetic flux. This decrease in magnetic flux will then create an electromotive force, causing current to flow through the circuit. Now, in the last video, I introduced how to determine the amount of the current that would be created, but I didn't talk about the direction of the current. So I introduced to you Lenz's law. Lenz's law states that the direction of an induced current is always such as to oppose the change in the circuit or the magnetic field that produced the induced current. So what does that actually mean? It means that an induced current flows in the direction that resists the change that created it. It's almost like the circuit knows that the magnetic flux is changing and will do whatever it can to prevent that change. It's a bit strange, so let's apply it back to our thought experiment. Remember that we are sliding the free end of the loop to the left. This will decrease the area of the loop. Now, since the area of the loop is decreasing, the magnetic flux is also decreasing. Now, Lenz's law states that the circuit is going to try to oppose that decrease. So if you recall from the magnetic flux formula, we can counteract the decrease in area by increasing the strength of the field. Well, Ørsted's law told us that electric current always produces a magnetic field. So this means that the induced current will flow in the direction that will produce a magnetic field in the same direction as the magnetic field that is already present. In our case, the induced current will flow counterclockwise. So looking back at the original illustration, the induced current must flow counterclockwise in order to increase the magnetic field directed out of the page. This is represented by the extra red field symbols pointing out of the page. We know this because of the right-hand rule. Look at any side of the loop. Point your right-hand thumb in the direction of the current and curl your fingers as if you are trying to grasp the wire. What you'll notice is that your curled fingers point out of the page everywhere inside of the loop. This will cause an increase in the magnetic field strength, counteracting the decrease in the loop's area. Lastly, let's imagine that we moved the free end to the right instead of the left. Everything would do the opposite, because the area of the loop would now be increasing. Since the area is increasing, the magnetic field strength would need to decrease to oppose the change in the magnetic flux. This is represented by the extra red field symbols now pointing into the page. Therefore, the electric current would need to flow clockwise in order to decrease the magnetic field strength inside of the loop. Thank you for watching my video on Lenz's law. I hope you find it helpful in your journey through electromagnetism. Please feel free to subscribe to my channel and follow me on social media.